Hello class, welcome to the first subtopic from the topic 1, which is 1.1 operations with numbers of the form a times 10 to the k, where the following requisites should be met, which is that a must be greater or equal than 1 and less than 10, and k, this exponent here, should be an element of the integers. I hope that you know by now that this symbology means what I just said. K is a number which is within or is an element of Z. And Z in mathematics, when you see a big Z, and it's usually written in this way, we have a double line in here. Usually you will see this. And by the way, this is part of the prior learning topics. So this is read as K is element or is an element of the integers, which basically says that k is an integer. Just a complicated way to say the same thing. So get used to the symbology, guys. It's there for you to help you, not to make your life worse. Okay, guys, so let's start this concept, this idea. First, I want to ask you a question. I want you to look at these two images. Let's look at this first. So we have a galaxy here, and as you know, there are quite a lot of stars in any galaxy that we know of. There are way too many stars. Now, suppose that you're writing an astronomical paper, or that you're writing an article about how many stars there are in the universe or the galaxy, I'm sorry, in this specific galaxy, and you find out that there are way too many, way too many. For example, we may say that there's 1 billion stars, and 1 billion is written in the following way. This is 1 billion, which is 1,000 millions. That's 1 billion. Okay, now, remember, you're writing an article about how many stars there are in the universe, and you're constantly gonna be talking about the amount of numbers that you have, about the number of stars that you have. So that's a lot of stars, guys. It's all of this. And suppose that you need to write down all of this number over and over again throughout your whole article, okay? Like 1 billion, and then you write some more, and then 1 billion, etc. It's too cumbersome. It's such a chore to be writing a big number like this all the time because it has too many zeros. So what people invented some time ago was a way to express numbers that are way too big or way too small in a much more compact way. Okay, so how do we write this in another form, which is a much more economical form? We write this: 1 times 10 to the 9. All of this number is exactly the same as this: 1 times 10 to the 9. If you do the mathematics here, if you actually calculate 10 to the 9 and you multiply by 1, you will get this number. Okay, so this is, guys, this type of notation is what we refer to as scientific notation. That's one of the names that it receives. Scientific notation. Also, some people call it exponential notation or exponential form. I'm going to go with notation. Exponential notation. Why? Because it makes use clearly of exponents. It makes use of a base 10 and some exponent in order to express large numbers in a much more economic way. So that's the name of this thing, and that's the way we're going to use frequently numbers, or that's the way we can express numbers frequently in order to deal with them, because writing a lot is not a good idea. Now, you must understand the following: the form of this notation, if you notice, is this one: a times 10 to the k. What that means is that you have a number, which let me write down here: a times 10 to the k. What that means is that you have a number in here, and then you have a times, and then you have a base, the base 10, it has to be base 10, and then you have the base 10 raised to certain exponent. and there are requisites, or there are characteristics upon, there are constraints upon each of these numbers, which are these. A must be greater or equal than 1 and less than 10. It cannot be equal to 10. It has to be less than 10. And also, k, like I said before, must be an integer. This k must be an integer. This a must be between 1 and 10, and it can also be equal to 1, and the base must be 10. That is the way in which scientific notation goes about. For example, if you look at a number in the written in this way, 2 times 100 to the 3. Okay, let's observe this number. The question is this number in scientific notation? No. No, why not? Because it breaks the form. You see, we have a 100 here, and the form tells me that you must have the number 10 as a base, not 100. So this is not scientific notation. Now, is there anything wrong with this number? There's nothing wrong, guys. Mathematically, it's perfectly valid. In fact, we can write this in scientific notation if we want, and we're going to do it in a moment. There is nothing wrong with this. It's just not scientific notation or exponential notation. Let me give you another example. What about 0.34 times 10 to the minus 2? Let's observe this number, and let's compare it with the form that we are given at the beginning, 8 times 10 to the k, where this must be true, and this also must be true. So, is this scientific notation? No. No, again. Why not? Because the form, let's say, breaks in this part. My a, which is this, is less than 1. In this case, 0.34 is less than 1. And we need a to be greater or equal than 1, not smaller. You see? What about this other part? Is the base 10? Yes. Is the exponent an integer? Yes. So these two parts comply, but not this part. And just if just even one part is not exactly in this form, then you discard this as a number in scientific notation. This is not in scientific notation. Once again, there is nothing wrong with this number, guys. This number is perfectly okay. It's just not written in scientific notation, and we in fact can write it down in scientific notation if we wanted to. So that's the idea behind scientific notation. It's a pretty economic way to write big numbers, or conversely, to write very small numbers. For example, now that we have this pandemic, we talk about viruses a lot, and as you may know, viruses are extremely tiny, extremely tiny. You cannot see these things with the naked eye at all. So these things are of the order of nanometers, and what that means is the following, guys. What that means is that the size of those things are approximately this big, 0.000000000, let's say 2 meters. That's how tiny it is, a virus. More or less, I'm not really giving you, it may be an order of magnitude less or more. This is just a rough idea of how small a virus is, you see? So whenever, for example, a virologist or a doctor, when they talk about viruses, about the size of a virus, they will never tell you that the size is 0.000000002 meters. They will never say that. It's too long. It's too long. Everybody's gonna look at him like, dude, what's wrong with you? So they will never use this. What they do instead is go back to the scientific notation or exponential notation, and they will tell you the size of a virus is 2 times 10 to the minus 9 meters. Because when we transform this into scientific notation, this is how it's going to look like. Okay, we have a number a, or that we may call a, which must be between 1 and 10. So is 2 between those two numbers? Yes, that's perfectly okay. And then we have times, and then we have a base 10. Can you see? And then we have an exponent, which must be an integer. And it can be either negative or positive. Remember, integers can be either positive or negative. There's nothing wrong with that. So this is scientific notation, and this is the way in which you would see the size of a virus written down in any scientific publication or any scientific article or anywhere. No one's gonna use this. This is very, let's say, it's very tacky. If you don't know what this word means, look it up in a moment. Okay, don't do this, guys, ever. Okay, so that is the meaning behind that is the, let's say, the reason why we use numbers, why we write numbers in scientific notation or exponential notation, because it makes our life easier by not writing down too much, and it has other advantages. Okay, fine. Let me erase all of this. So now that we know the reason behind writing numbers in scientific notation, let's actually go over how we transform a number which is not in scientific notation. Let's write transforming numbers to scientific notation, because that's what I want to know. Scientific notation. That's what I want to know. How do we do that? For example, what if we have the number 3700 or 3700? This number is not written in scientific notation, so let's write it down in scientific notation. And remember, the shape will be some number a times 10 raised to some exponent, which should be an integer. So what is the way we go about this? What we do is this: you're gonna locate the decimal point of your particular number. The decimal point in this one, since it's an integer, is located right here. All right, and then you're gonna move that point either leftwards or rightwards as many places as you need until you encounter a number between 1 and 10. So let's do it. So we move one place, I'm sorry, and now we have the number 370. We move it once again. We have the number 37. We move it once again, and we have the number 3.7, which is between 1 and 10. So I'm gonna stop right there. And I'm gonna observe the number that I came up with, which is 3.7, and that's the number I need to put in here. 3.7 times 10, and what's gonna be the exponent right here? Well, it's gonna be the number of places that I moved, in this case to the left. So it's gonna be 3. Okay. Now some people are gonna ask, how do I know whether this exponent should be positive or integer? Fine, that's a good question. The idea is this: if you move the point towards the left, okay, you're gonna have a positive integer in there. That's the idea. So to the left, that means a positive integer. Fine. Now there is a reason for this. It sounds like a rule out of the blue that I'm just creating. No, there is a reason for this, which I'm gonna explain in a moment. First, I want to teach you how to do it basically. Now B, how about this number? 0.00021. Okay, so we have this number. It's not written in scientific notation, so let's write it down in scientific notation. We need to write it down as some number a times 10 raised to an integer exponent. Once again, locate your decimal point, which is right here, and move either to the left or to the right as many places as you need in order to encounter a number between 1 and 10. It's very simple. So we move 1 point, 1 place, 2 places, 3 places, 4 places. And I'm gonna stop right there because now my number reads 2.1. And I'm gonna stop right there. So the number that I will place in here is 2.1 times 10. And then here, the number of places that I displaced, which was 4, 1, 2, 3, 4. And is it going to be positive or negative? Well, in this case, we move the decimal point towards the right. And when we move towards the right, that means that we have to write a negative integer. So I'm going to write -4. So that's how it works, guys. Now, let me tell you the reason why, this rule works, so to speak. Okay, let me explain it with this number, 3700. So we have 3700. How can I actually produce this number in scientific notation without, well, let's say with a much more reasonable approach, or much more logical or meaningful approach? What do we do? Okay, what we do is this. You can divide and multiply this number by the same uh, number without altering it. I'm going to repeat what I said. You have this number, and you can at the same time multiply it and divide it over the same number, and you won't be actually altering it. You see, for example, if I multiply this number by 2 and at the same time I divide over 2, then nothing really is happening to this number. Nothing at all. You see, because I'm basically multiplying by 1. This is 1. That's the reason. So what you can do is this. You can multiply by powers of 10 and divide by the same power of 10. Basically, what you can do is this. You have this number, and as you know, when we divide this number over 1,000, we can get to a number. We're gonna get a number, which in this case is 3.7. If I divide this over 1,000, we know that we will get 3.7. Is that right? I think we understand that since primary school. So we need to divide this number over 1,000 to produce this number that already has the same the requirement for the a, because it's between 1 and 10. Now, I cannot just divide this number over 1,000 and be done with it. That would be incorrect, because I cannot change this number. I'm just going to re-express it in scientific notation. So in order for this to actually be equilibrated, what I need to do is not only divide over 1,000, but also multiply by 1,000 at the same time. Well, let's actually write it down in this way. We're going to divide over 1,000. This is a full line, a straight line. And at the same time, we multiply by 1,000. That's what I'm doing. Multiplying by 1,000 and dividing over 1,000 at the same time. Now, if I continue with some algebra, I can actually just do this, like the division over 1,000 goes with this number, and then times 1,000. Now, how much is this? This is going to be 3.7 after you perform the division, and then you remain with this 1,000 here, and then finally you can just re-express 1,000 in terms of an exponential form, which will be just 10 to the 3. That's very simple to understand, right? And that's it, guys. That's how we can convert this number into scientific notation with logical operation, with a logical method. What we're doing basically is multiplying and dividing at the same time by the same power of 10. In this case is 10 to the 3. You see? Now, what about this? 0.00021. If we know that if we multiply this number by a power of 10, which is in this case 10,000, then the number, this decimal will be displaced 4 places to the right if we multiply by this number. Okay, so why not doing it? Let's do it. This number times 10,000, you see, and at the same time I need to divide it over 10,000 in order not to change this number. So what's going to happen when I multiply this times 10,000? What am I going to come up with? I'm going to come up with 2.1 over 10,000. If I recur to the exponential form, 10,000 is written as 10 to the 4, 2.1 over 10 to the 4, which is equal to 2.1 times 10 to the minus 4. Why? Because remember that if we have a fraction and in one of the places of the fraction we have a base raised to an exponent, you can move the base to the other side of the fraction as long as you change the sign of the exponent. You see? So I'm moving this 10 to the 4 upwards, and it's going to convert into times 10 to the minus 4. So that's why this number can be written in this way by using this multiplication by 10,000 and division over 10,000. That is the logic behind it. But if you just want to use this rule of moving points, that is perfectly okay. That is just nice. You don't have to do all of this stuff. Okay, fine. Now let's go over addition. Addition of numbers in scientific notation. Addition and subtraction, that's pretty much the same stuff. Addition and subtraction. For example, what if I gave you these numbers? 2.3 times 10 to the 4 plus 3.2 times 10 to the 4. How do you add these two numbers without the calculator? You're not going to use the calculator at all in this topic. So what we do is this. It's a very simple idea. If you notice, we have this number times this factor. Try to look at this as a factor, and in here we have the same 3.2 times 10 to the 4. So we have actually these two numbers, all of this number and all of this number share a common factor, and that common factor is 10 to the 4. So why not we take it out as a common factor? So we have 10 to the 4 that multiplies 2.3, because if I multiply this times this, I get all of this, right? And then plus 3.2, because 10 to the 4 times 3.2 gives me all of this number. You see, I just performed a factorization. And now that I have performed that factorization, look at what you have inside the parentheses are two numbers in decimal notation or standard notation, which you can add. 2.3 plus 3.2, you're going to get 5.5. So you're going to get 10 to the 4 times 5.5, which is basically the same as 5.5 times 10 to the 4. So we go back to the classic notation. This is already scientific notation. We're not just writing the times, but it's the same. Okay, so we have this. That's how you do it. Now, what is the problem when we encounter a number like so? For example, we have this 3.1 times 10 to the 4 minus 2.5 times 10 to the 3. Now we have two numbers in scientific notation, but they do not share the same exponent in the base. You see, you have 10 to the 4 and then you have 10 to the 3 in here. What is the solution in this case? What can we do? What we do is we're gonna re-express one of these two numbers, either whichever you want, into the exponent of the other one. For example, let's try to express this number as a number which is written as something times 10 to the 3. That's what I want to do. That's what I want to do. Okay, so let's do it. Or, well, no, there is a better way to do this now that I think about it. You can do this, guys. You can look. Oops. You can look at this exponent, 10 to the 4. And you can see right away that this can be written, 10 to the 4 can be written as 3.1 times 10 to the 1 times 10 to the 3, right? 10 to the 4 is equal to 10 to the 1 times 10 to the 3. I hope you can remember that, how to sum exponents. So basically, all of this is the same as all of this. You see? Now, what is the common factor between these two numbers? Between this number and this number? It's going to be 10 to the 3, quite clearly. So let's take it out as a common factor, 10 to the 3, that multiplies 3.1 times 10 to the 1 minus 2.5. Okay, now what we do is 10 to the 3. What we do is let's convert this number into standard notation. 3.1 times 10 will be just 31 minus 2.5. Now that we have these two numbers in standard notation, let's actually perform the subtraction. And that's going to be 28.5 if I'm not mistaken. No, it's going to be 29.5. Or is it 28? 28.5, 29. No, yeah, it's 28.5. That is the correct subtraction. And we're done. Now we just reshape it as 28.5 times 10 to the 3, as you can see. But just realize that this number, we have performed the whole subtraction, but you must realize that this number that I came up with at the end is not written in scientific notation. Why not? Because this number is not within 1 and 10. So you need to change that. How are you going to change that? Okay, let's stop right there, and I'm going to ask you live, because I just get bored of you not talking, and I need to ask you some stuff. So let's pause it right there, and I'm going to ask you how we can transform this into scientific notation. So let's stop the lesson right there.